Chapter 7 is periodic properties, periodic trends. First of those is atomic size. In general, you get bigger going down the column and you get smaller going across the row. That's because you get smaller across the row because of an electron screening effect. You have more electrons screening those outer electrons from the full charge of the nucleus. Therefore, you get an effective nuclear charge that's less than the actual nuclear charge. You can see this a little bit more graphically. You can see hydrogen's pretty small, but as you go down the column, they get big. But as you go across the row, they get small. You don't have to memorize the numbers, but remember the trend. So as a general rule, it's going to decrease from left to right as you move across and increase from top to bottom. So let's consider each of these and decide which of these are the biggest in terms of atomic size of our neutral atom. Now you got selenium, sulfur, oxygen, tellurium. Those are all in the same vertical column, where oxygen's on the top, so therefore would be the smallest. Then sulfur is beneath it on the column, so it would be the next biggest. And then if you keep going on the column, you got selenium and tellurium. And so you can keep going down the column that way. And that's in group 6, or excuse me, 6A. So you can actually see that work out. Now, if you look at the other one, you got phosphorus, chlorine, sulfur, silicon. Those are all right next to each other in the same row. They're on that third row of the periodic table. Now remember, it decreases in size from left to right. So the thing the farthest to the right on the periodic table would be the smallest. The smallest thing, therefore, would be the chlorine. And then as we go across, we've got sulfur is next farthest over. And then phosphorus. And then silicon would be the biggest. And that's in that third row on the periodic table. Ionic radii. Ionic radii have the same basic trends as atomic radii, except you have to make adjustments for the positive and the negative charge. Cations are going to lose electrons, so you got fewer electrons than protons, and therefore it's going to shrink in a little bit and be smaller than the neutral atom. Anions, you're going to add extra electrons, so electron-electron repulsion gets bigger. So it'll spread out to minimize that repulsion. The effect is going to be a larger ion than the neutral ion. But you see the same basic trend occurs as if you're looking at cations and anions, but if you mix and match, you have to be really careful. So if you got sodium versus magnesium versus aluminum, you see the neutral atoms get smaller, but the ions also get smaller. But you see that the sodium is smaller than its neutral atom, the magnesium is smaller than its neutral atom, aluminum is smaller than its neutral atom. Now, you can see things get bigger with negative charges because that nitride is a lot bigger than the nitrogen atom, so on and so forth. But you can see the nitrogen, oxygen, fluorine gets smaller as you go across the row. But then nitride is bigger than oxide, which is bigger than fluoride because, hey, the ions are bigger because they have bigger charges. And so you have to consider that. So if we want to consider these based on ionic radii, so if we look at the schematic on atomic size and try to answer that question, you see you got chlorine, sulfur, selenium, bromine. So if you look at it, the bromide is just a little bit bigger than the sulfide. So now we can say for that answer that it's chlorine, then the sulfide, then the bromide, and then the selenide would be the biggest. And you can see the positive ion or the negative ion are in color, and the neutral ions are in gray on that particular chart. Just looking at a couple. Lithium loses 1 electron to form lithium +1, and it does reduce in size. Fluorine gains 1 electron and increases in size. Ionization energy. Ionization energy. The first ionization energy is the amount of energy required to remove that first electron from a gas phase atom. For example, that magnesium, I'm going to have to put in 738 kilojoules per mole to remove that first electron. If I want to remove the second one, then it's going to take me 1451 kilojoules per mole. And you can have ionization energies all the way until you're done with electrons, but what you're going to find is that the more electrons you remove, the higher the ionization energy. Once you're out of valence electrons to remove, it's going to get disproportionately more expensive. Turns out group 2A and group 5A have unusually high ionization energies because of that. You've got a full shell in the 2A, that S shell is full, and then 5A, that P shell is half full, which creates some dynamics of that not being the case. So in general, though, you're going to increase from left to right and decrease as you go from top to bottom. And you can see this sort of graphed out. You can see the 2A there and there is higher than you would predict, and the 5A is higher than you would predict. Maybe a diminishing effect there, but still higher than you would predict. So we'll use this graph and we'll kind of answer the questions. So here we've got things in the same column. That's not going to be too bad. Okay, let's look at these. They're all in the same column, so the top of the column is going to have the highest ionization energy. The bottom of the column is going to have the lowest ionization energy. And if we kind of look, we can kind of still see it there on the graph. Magnesium is going to cause us maybe just a little bit of a blip, but since everything's in group 2A, it should be fine. So we start at the bottom of the column, which is going to be strontium, and then calcium, and then magnesium, and then beryllium would have the highest ionization energy. Now, this next one takes advantage of all the blips in the trend for that second row. So it's not just a left or right thing. So you got beryllium, oxygen, boron, nitrogen. But if I look at it, you would expect oxygen and nitrogen to have a higher ionization and beryllium and boron to be lower. But the lowest is going to be boron, then beryllium, then oxygen, then nitrogen, because you got the blips at 2A and 5A. So if we type that in, so it's going to be beryllium, then boron, then oxygen, then nitrogen. And that would be the trend there. So if you look at it again, removing those core electrons is progressively more expensive. Those reds represent removing of a core electron. Sodium, you can lose one pretty easily, but that second one's kind of expensive. Magnesium, I can lose those first two pretty easily, but ooh, that third one's expensive. Aluminum, I can lose three, but ooh, ouch, that fourth one's expensive. Silicon, nice smooth increase, so all four of those were likely valence electrons. The ionization energies we can use to predict that stable ion formation because removing the core electron is expensive. And so we find that they tend to form the nearest noble gas configuration. Sodium, magnesium, aluminum tend to all lose their valence electrons to be isoelectronic with neon. But phosphorus, sulfur, chlorine all gain electrons to become isoelectronic with the next noble gas, which is argon. And so we can predict which ion might be stable. And again, if they have the same electron configuration, we say they are isoelectronic. Here is a series of ionization energies. So what would we predict the charge on the ion to be? We see the ionization energies go up pretty smoothly till we get to the 7th one, but the 8th one is significantly more expensive. So I would assume we'd have 7 valence electrons, and then therefore the charge would be a -1 because it's in group 7A. All right, so let's talk a little bit about electron affinity. That's the amount of energy absorbed when an electron is added to an isolated gaseous atom to form a -1 charge. Now, these can be endothermic or exothermic because it's just the energy associated with gaining the electron. Ionizations are always endothermic. But generally, things that are positive or greater than 0 are tougher ions to form. Not that you can't form them, but so magnesium gaining an electron requires 231 kilojoules per mole, or your electron affinity energy is a positive 231 kilojoules per mole. That's 2A generally has a positive because it's got to put an electron in a higher energy level orbital. Noble gases and group 2A tend to be positive. Most everything else minus, even if it's a small minus. But in general, again, group 2A and 5A have more positive, or at least less negative, electron affinities than you would expect. But as a general rule, it's going to get less negative as you go towards the bottom and left, and more negative towards the top and right, excluding the noble gases. Noble gases are all positive. So in general, this is what happens. Anything that's positive, I just plotted as a 0 for this particular graph. But you can see your noble gases, nitrogen, your group 2A elements were all plotted there at the top. And then everything else is below it showing negative. But as they get towards that top and right, things get really negative. Another blip in the trend is the chlorine tends to be slightly more negative than the fluorine, although the trend would not tend to indicate that. So if we kind of compare that to the chart, we got sulfur, magnesium, silicon, and sodium. So if we look at that, you got sulfur's there, silicon is there, magnesium's up here at the very tip top, and then sulfur, silicon, magnesium, and then sodium is slightly more negative. And you notice those are all in the same row. So since sodium is the farthest to the left on the row, you would expect it to be sodium to be least likely to gain an electron, but no, it's magnesium. So least likely magnesium, then sodium, then silicon, and sulfur being the most likely to gain an electron. So if we want to move down here, now that we've looked at the trend, we can say magnesium is least likely to gain an electron, then sodium, then silicon, and then sulfur. And that's all based on position on the periodic chart. Electronegativity we'll talk a little bit more about in the next chapter as we start doing Lewis structures and polarity of molecules and things like that. But electronegativity is the tendency of one atom to withdraw the electrons within a bond towards itself. Based on the Pauling scale, fluorine is the most electronegative, cesium and francium are at the least electronegative end. As a general rule, things are bigger at the top and right, excluding the noble gases, and smallest at the bottom and left. Some of these noble gases don't have any compounds that are known, so they're empty. These two noble gases have known compounds, and so there is a electronegativity for them. But you can see they're all in this particular chart, and you can refer to it. For this test, I just expect you to know the basic trend. For the next test, when we start talking about polarity of molecules, we'll need the actual numbers, and I'll give them to you on a chart. Not for this test, but for the next test. So if you arrange these based on the electronegativity, you can see there's selenium and germanium and bromine and arsenic. So we can see that germanium is the smallest, then arsenic, then selenium, and then bromine. So if we write those out, we got germanium, selenium, or excuse me, arsenic, then selenium, then bromine. And that would be your ordering in this particular case.